And to tell you the truth, when I got the feedback of the students last year, mostly petroleum students, they said that this course was very useful. Okay. So, and also they were even wondering why this course was not offered earlier. Okay. But anyway, but the point I'm trying to make here is that this is actually probably a course which would be beneficial to, in general, any engineer. Okay. So just keep that in mind. Okay. All right. So what is this course all about? Well, there are three things. Okay. Modeling, simulation, and optimization. Right? So I'll just quickly tell you. And actually, to cover all of the three things in detail would be very difficult in one semester course because optimization itself is a separate course. Okay, so that is like a semester long course. So I will try to do. I'll try to optimize the course. Okay. So and probably just touch upon some important ideas I may need to, but some things I will spend in details. Okay. So modeling part. What do these three words mean? Okay. So modeling, simulation, optimization. Modeling essentially implies what is inherent in there is actually it's mathematical modeling of a process or phenomena. Okay. Any any occurrence, anything that's occurring, if you try to extract the basic mathematical equation that can be used to that which actually governs the phenomena. So basically, it's an extraction of equations. Okay, which govern the process. Okay, so this essentially this is where mathematics becomes necessary. Okay? And especially the applied parts of applied mathematics becomes useful over here. Okay. Now, once you have extracted the mathematical equation that governs the phenomena, okay, then you want to implement them. So basically, you solve them and see what you get experimentally is what you get from your model. Okay, that part is called simulation, implementing the model. So simulation is essentially implementing the mathematical model. Okay, so the purpose is to check whether your model is good or not. Okay, so the main purpose of simulation is, so idea is to basically validate your model. Okay, so whatever assumptions you have made, whatever mathematical equation you have come up with to kind of mimic the process. Okay, so when you say that, okay, this is the equation that mimics the process, therefore this should give me the correct result. So so how do you know this should give you the correct result? Well, you solve it and then look at the result that you expect from your mathematical model or mathematical governing equations and compare with the experiment. So when you actually implement that mathematical model or solve it, implementing means solve, basically. Okay. So, and then you compare with the experimental results, you actually try to validate your methods. This implementation part is called simulation. Okay. And optimization. So optimization is what does it concern? It concerns, as the word suggests, in a very complicated process, there may be several parameters parameters of interest, right? There can be, so for example, if you have any transport process, okay, you can have lots of different kinds of parameters. For example, conductivity, diffusivity. If you're looking at both mass and momentum transfer and heat transfer, everything happening together, then you will have lots of parameters like diffusion coefficient, thermal conductivity, heat capacity, thermal potence, viscosity, and density, those things. So those a lot of parameters will be there. So now with those set of parameters, if you're given a free will to achieve some desired result, and you say that okay, you get me this result, tell me on to get this result. So you would require, for example, if you want the heat transfer coefficient to be minimized under certain conditions, certain settings, then you may require, if you have a bunch of possible options to choose from in terms of fluids, okay, then which fluid will you choose? At what velocity would they flow? What would be their viscosity? What would be their density? So you need to optimize you need to get the best result in the given with the given in the given circumstances. Okay, so so basically, that's what you can do. So once you have the model in place, okay, once you have a model in place, you can simulate it, okay, then you can play with the model. Okay, you can actually, and once you've simulated it and validated the model, said, okay, my model is good enough for my own interest, okay, then you can basically then try to get the optimal set of parameters which would give you desired results. Okay, so that's where the optimization part comes into picture. Okay, so to optimize the physical parameters, okay, to achieve the desired result. So that is the overall idea. Okay, you you have a process, you extract mathematical equations governing it, you implement it, okay, you solve it and test it with respect to your actual physical results. And then once having done that, then you, if it tests well, the model is validated against your real life result. Okay, then you try to then you ask the actual problem. Okay, now what do you want with this? And then suppose you know what is to be what if you want a maximum profit, let's say, from a given plant, so then you will accordingly play with those parameters so as to get optimal desired profit, let's say, for purity. It can be so whatever you want, it can be your concern. But once you know what you want to optimize or maximize or minimize, then in order to get to that optimal result, how do you set your parameter? Okay, this would be like a search in optimization is essentially search in parameter space. So this frequently concerns class delivery. Sorry, all right, 12:30. So, so this is essentially this very frequently involves search in parameter space. Okay. So, okay. All right. For this will give you a very probably a very well-known example. Suppose you have let's see, I think as far as I remember, this was one of the JE problems used to be. There was a stick live there, and then you can actually adjust its theta. And for some value of theta, it's potential. It basically what was the problem? Something some parameter optimized maximized with respect to theta. So basically, there you had to search, you had to basically optimize or minimize or maximize a function with respect to theta, right? So anyway, I'm sorry, I couldn't recall the exact problem, but essentially what you had there was a function had to be minimized or maximized with respect to a variable, minimized or maximized with respect to a an argument. And you have already you already are aware of this, or already are aware, in the sense that you already know if I have a function of one variable, okay, then how to get the optimal value of the function, right? Just take the derivative, set it to 0, and whether it's maximum or minimum, you would know from the second derivative value, right? Whether it's positive or negative. So that is standard, very simple first thing that you learned uh, in your class 11, 12, right? But what we will look at will be if you have uh, when you cannot just solve the derivative, if you set derivative to 0, and then the equation that you get, you are unable to solve analytically, let's say. Okay, then what to do? Or if you have a function which is having a bunch of variables, okay, not just one, but several variables, and then you're free to tweak all those variables and then find for what set of values for those set of variables, what values for those set of variables would you get the function to be to achieve maximum or minimum value. Okay, so in that case you have a function of several variables. Okay, you can also have multifunction, multiple optimizations. Okay, so those are the kind of more complicated scenarios in when you talk about optimization. Okay, so we'll talk about those things when we talk about optimization. Okay, okay. Now, okay. So first thing, now when we talk about modeling, I expect you to be familiar with when you model a physical phenomena, there are certain basic ideas based on which we model, right? So modeling part is based on basically based on some natural laws, right? Natural laws, which are essentially conservation laws, right? Conservation principles. So whatever happens in nature, whatever process occurs, it has to be such that it respects some conditions, right? Those conditions are, uh, those conditions have been basically outlined by our, by basically they have been outlined from based on our scientific understanding, right? So those are the conservation principles, which are essentially mass conservation, momentum. Well, momentum is not conserved, but basically momentum is basically Newton's laws. Okay, and energy conservation. Okay, these three these three are basically uh, these three important ideas are helpful in modeling of phenomena, and they concern the physics of the. Okay. Similarly, you can have chemical reactions. So kinetics equations. So if you have chemical reaction going on in kinetics, okay, will be actually governing the your process, right? There will be another mathematical, can say some kind of mathematical principle or equation based on certain chemical principles that govern the phenomena. So that would be useful. Okay. So basically these will form our working principles based on which you can do mathematical modeling. Okay. All right. There will be more. We'll meet more of those physical principles. So these are basically This kind of modeling is called, it basically falls into a category where you say that it's based on physico-chemical principles. Okay, you just apply these ideas to any process, and then you get to extract the mathematical equation governing the process. And they very frequently give something known as deterministic models. Deterministic models. Okay. What do I mean by deterministic models? Well, you can precisely, I mean, when you implement the model, you'll get a single answer. Okay? You'll get some fixed answer for whatever you want to find out. Okay? Any quantity that you want to basically calculate based on your model, you get a definitive answer. Okay? This There are certain cases where you may not be able to get the definitive answers, okay, in reality. Okay, so what you do is those kind of, so you also, there are certain models which are based on statistical modeling. Okay, so that's called stochastic models or statistical models. Stochastic models. Okay, so stochastic models, they do not give you uh, don't give precise answers, precise values, okay, or precise values. What instead you do here is actually you get a mean and variance. Okay? So you can get a distribution, okay, for your predicted or the quantity that you want to actually compute, okay, or calculate, okay, or predict. Okay, so quantity to be calculated. So you get mean and, well, actually not just mean, but you should say you get the distribution function. Okay, you get probability distribution function. Okay, so for example, this is very frequently used in let's say finance. Okay, so if you have some commodity whose price can be like petroleum product prices, right? So they are fluctuating quantities. So all you want to do is you may not be able to get a precise value, but your model will give you that, okay, this would be your price will be having this kind of spread, okay, and this kind of peak around certain value. That is called distribution function. So when you try to solve for the particular distribution function. Okay, so these models actually tend to basically they are aimed at solving the probability distribution. Okay, so they are also closely related to something called particle-based models or population balance-based models. They're closely related to something called population balance-based models. Okay, so what happens here? So actually, somewhat closely related to stochastic models. So, for example, if you have, say, a process where you have a flow, okay, and you have lots of bunch of particles here, they are constantly uh, coming close to each other. They are fragmenting, they are coalescing, fragmenting, etc. Okay, so particles, these are particles in the flow. They are constantly coalescing or fragmenting. Okay, so on. So these are they tend to stick sometimes, and then as the flow occurs, they disintegrate, and one particle give rise to two particles. So based on that, particle density will be changing from point to point. Okay, so there also you tend to find out how the density changes at different points in the flow of density of particles. How many particles are there per unit volume, let's say, at a particular point in this flow, right? So there you basically try to look at the population of particles in a particular volume and then try to predict that population, right? So those are population balance based on. Okay. All right. So okay. Now um, let me just give you certain examples. So So first uh, we'll talk about the models based on chemical principles. It's just I'll spend some time over here. By the way, before that, I just want to state that I just want you to be. Let's go back to here. So here, this part we'll talk about in pretty detail, right? Mathematical modeling part, right? For different kinds of processes. This part, implementation part, now here I want you to learn MATLAB. If you have already not done that, please do that. Okay. So this course will be heavily relying on MATLAB, and this is software which is available to us, our institute. We have subscribed to it. You talk to IT people, Mr. Anil Verma. He will help you in installing it on your laptops. Okay. Please get it installed and uh, just learn it. I'll probably spend a couple of sessions just for the sake of helping you guys. But it's not part of the course. But still, I would spend maybe a lecture or two on telling you more about MATLAB. But you are supposed to learn by yourself. This is simple, very simple. There are a bunch of videos, tutorial videos available on YouTube. Right? Check them out and listen to it. Okay. All right. So that's one thing you should start. If you do not already know MATLAB, start learning it from today now itself, right after this class. Okay. Because otherwise, this course will be of no use. Okay. Do learn MATLAB. All right. So moving on. So first kind of mathematical models based on physico-chemical principles, which are basically uh, conservation laws, right? Basically speaking, most of the equations are based on a very simple rule. Okay? Uh, First of all, mostly we'll involve transport processes, right? In generally things we will be interested in modeling would be one kind of problem will involve a broad class of problem will be concerned with transport processes. Can have thermodynamics related problems with thermodynamic modeling. Okay, this would be concerned with equilibrium. This would be, so right hand side would be basically equilibrium. Right? This would concern equilibrium behavior. This would concern flow behavior. That's it. I think mostly the problem can be classified, especially in chemical engineering and petroleum engineering as well. These two kinds, right? Okay, so I'll come back to this later. Let me first talk about a little bit about transport processes kind of problems, okay, which involve transport problems, which involve transport processes, right? So, okay, now basic idea is very simple. The basic conservation rule is rate in, minus rate out plus rate generation, okay, okay, equals to rate of accumulation. That is the governing rule. Okay, all the equation that we will see will fall into this category. Okay, now let's see. Let's start with a simple case of. Okay, so now this is the conservation rule, conservation laws. Okay. Now these conservation law, this is a conservation law. It's a law of the nature, right? This has nothing to do with a particular material. All right. So this is natural law. Natural law. Okay. Material has no role to play. But how do you basically incorporate material behavior in your model? Okay. There are, in order to basically incorporate material behavior. Okay. Incorporating material behavior. You will be having something known as constitutive relationship. I think this is it. I taught you. Did I teach you fluid mechanics? I think I taught this class fluid mechanics, so I think you shouldn't have it. You don't recall that course. So constitutive relationships are combining conservation law and constitutive relationships together. You'll get a so basically you get a model. Okay? The model has essentially two important or the models based on physico-chemical principles have two important ingredients. Okay, one is conservation laws and the other is constitutive relationship. Okay, so how the material behaves under certain circumstances. Okay, that relationship would be that mathematical form of a relationship that tells me the mathematical form of the relationship that tells us how the matter material behaves under certain circumstances. Okay. So well, you all know what the constitutive relationship, the examples of constitutive relationship. If I compress, if I elongate something, it will expand. If I compress something, it will shorten. Okay, so that's elastic. If you look at mechanical behavior of something, how it mechanically responds to applied forces, that would so F equal to kx, for example, for spring, this is a constitutive relationship. Or sigma equals to epsilon e, that's a constitutive relationship. And that would be for the mechanical behavior of solids. For fluids, the sigma equals to mu gamma dot. That would be a constitutive relationship. Okay. Another kind of constitutive relationship could be rate of reaction. Okay. So R equals to minus K C raised to N. Okay. Rate of reaction is nth order. That is how material behaves. Okay. That's another constitutive relationship. Okay. V equals to IR is another constitutive relationship that tells me how it will behave under given voltage, what would happen, what kind of electrical behavior will it manifest. Okay, so those are the kind of those are the basically, so all those relationships that reflect material properties, okay, are known as constitutive relationships. Okay, so these reflect material properties, or reflect or define, I should say, define certain material properties. Okay, so basically, for example, this defines spring constant, this defines Young's modulus, this defines viscosity, this defines rate constant, etc. Okay. So, all right. Now, so basically, the again to remind you, a model consists of two components. One would be related to conservation laws, and other would be constitutive relationship. Okay. Now let's see examples. Suppose I have, well, you all probably know this, that if I have a diffusion, okay, so diffusion. So diffusion will be to do the balance. So uh, let's say one-dimensional diffusion. Okay, so you think of the slab, okay, and rate in minus rate out. Rate in would be basically, so J X, J is the flux, okay. So G just G. Yeah, assume this X direction. This is X direction. So J into area, okay, and X. This is my X. This is X plus delta X, okay. And diffusion is occurring across this. So so the rate in would be JA and X minus rate out JA X plus delta X. Okay. So if there is a diffusion occurring, only diffusion, okay, and because of diffusion, there is a flux. Okay? A flux. So since this is because of diffusion, let me call it J sub D. And J sub D, J sub D. Okay. So this means diffusive flux. Okay. So it's a one-dimensional case. So I have only x changing. So from x to x plus delta x, I have diffusion, the net rate. So in time delta t, okay, I'll have, let's call this unit time delta t is equal to 1. Then j into a into 1 would be entering this side and leaving this side with minus this. Okay, and that would be equal to what? That would be equal to total rate, total change, okay, that is delta n. So let's say, but we can do delta t over here. So by delta t, I will have x. Okay, so that would be equal to delta n. Okay. So you all know the derivation here, but I am just doing for the sake of completeness. So delta n I can take to be concentration into area into delta. So this is the concentration. Okay. And the reason I do it because I want to get rid of area term. Because area should not matter, it's a one-dimensional problem. So whichever area is constant everywhere, so we will assume that area is constant. Area is not going to. Well, 12:45. Oh, I see. It's already 12:40. Okay. I'll stop here. I'll just quickly stop here and then. I'm sorry about that because I just started so late, so I just keep track of time. I'll just quickly finish it. Thanks for reminding me. Just give me one second. So that would give me del by del x dv. Okay. So I just do delta t on this side, write delta n is equal to this concentration into volume. Okay. That would give me with a minus sign, of course. So delta, so that would give me a cancels out. Okay. Should be delta x over here as well. Delta x cancels out, and I get minus del by del x e equal to del c by del t. The limit x in t tends, delta is equal to 0. This you all know, this is a conservation principle. This is basically conservation principle. Okay, and then you combine this with constitutive relationship. This is not done. I mean, we have not yet achieved a model, working model. I have to use the constitutive relationship. Yes. What is that constitutive relationship? Constitutive relationship tells me that JD should be proportional to del C del X with a minus sign. Okay, that's Fick's law. So Fick gave us this constitutive relationship, that is JD equals to minus D del C del X. Okay, so when you plug this in over here, I get a working model for diffusion for the processes involving diffusion only. Okay, And that is information that we all know, okay, which is del by del x, okay, d del c by del x equals to del c del t. This is a mathematical equation that will be required to find c as function of x and t. Okay, I'll stop here and we'll start tomorrow again. Okay, we'll meet tomorrow again. Bye bye. Yeah. I will. Okay. You joined late. Fine, fine. That will be done. Sure. I will share the video lecture. Okay. But the only thing is that since you joined late, I guess the ID which has been given to me from the IT section has something wrong with it. So once that ID is basically clarified, then I will share on that with that particular ID so that all of you can actually share it. So I think the ID that has been given to us, on which I sent the invitation for today's lecture for chemical students, that was not bona fide. Okay, there was some problem with that. So that has to be ensured first. And then I'll share with that particular ID on the Google Drive, on the particular Google Drive. Okay, and you can just look up. All right. We'll meet tomorrow. Bye bye.